Let's welcome Dr. Joel Dudley.
All right, guys, we're almost done. All right, almost there. So you guys are the most hardcore science fans. This is great. I get to talk to you. You stayed the longest. So it's a good thing you also have an American from New York talking last because I'll talk very fast. So here we go. So these are two main questions that really drive a lot of my research. What is health and what is disease? And I'm going to argue that we really don't have satisfactory answers to either of these questions. In fact, I think we're just starting to be able to answer these questions based on some of the recent technologies that have been developed. I know this is an event that's about the future, but I'm going to start by going way back to the past. So some of you might be aware that there's this book that's over 2,000 years old, a Chinese text in English called The Inner Canon of the Yellow Emperor. This book presented several really interesting ideas, especially for the time, but I would even argue interesting ideas for now. It introduced the idea that health could be assessed by rational observation of symptoms, of characteristics, not spirits, which were used to diagnose disease at the time. And it actually suggested that man was a microcosm, similar to a macrocosm of the environment, where you have all these different forces that are interacting in complex ways, and you would assess health rationally and objectively by looking at the interplay of these forces, and that disease was an imbalance of these forces, and to restore disease, or to restore health, you'd have to restore the balance. Western medicine, on the other hand, is sort of founded on this disintegrated view of health and disease. Now, obviously, Western, or so-called Western medicine has made great advances in health and improving the health of people around the world, but it's kind of unusual, from my perspective, if you walk into a modern hospital, you'll really see that the way that the health is treated is broken apart by the anatomical system, right? So of the body, we have pulmonologists for the lungs, nephrologists for the kidneys, etc. I mean, veterinarians have to treat multiple species, right, under one roof. But for some reason, when we treat humans, we treat the different parts alone. So, and our understanding of the body has really been accelerated by molecular biology, but this has also taken us further down the path of this reductionism. So there was a really important discovery made by a Shanghai-born professor, Dr. Sui, who was a scientist who was working in Canada at the time. He was studying a disease called cystic fibrosis. Cystic fibrosis is an inherited disorder. At the time, it was very, very lethal. It's still lethal today. So it was killing children at the time, but it still will kill most people affected before the age of 40. It's, again, an inherited genetic disease, which predominantly affects the lungs. And both parents have to carry the genetic factor. And you have organ failure and things like that. What Dr. Sui did back in 1989 was use the emerging powerful tools of molecular biology to discover the gene that was causing cystic fibrosis. He discovered a gene called CFTR. So all of cystic fibrosis is explained by mutations in this one gene, CFTR. But even though one gene causes this disease, what that figure on at least my right here is showing is that this mutation in this single gene can manifest in the body in very complex ways. It can affect the lungs, the pancreas. If you have other genetic factors, it can change how the disease is expressed. But one key thing that I like to point out on this slide is that we've known that mutations in this single gene have caused the disease cystic fibrosis for almost 30 years now, and we still can't cure the disease, right? One gene, one disease, 30 years later, we still can't cure it. Why? Well, in fact, we've found thousands of such disease genes, right? Where we know the gene that's causing the disease, but we still can't treat the disease. Why is our ability to discover disease genes really so far ahead of our ability to translate it into knowledge and into therapies? Well, one reason behind that is that humans are not a machine like a car or a computer, right? That these sort of deterministic sort of systems. We're complex adaptive systems. Human beings are complex adaptive systems. It's a very sort of well-described type of system, say in mathematics or physics. And there are important characteristics of a complex adaptive system, that they change over time, that there's interactions, that the whole is greater than the sum of the parts, and you cannot understand the whole system by looking at its individual parts. But what we continually try to do in biology today is we try to understand the parts and understand the system. But we know we shouldn't be able to do this very effectively in a complex adaptive system. By the way, who said this quote? It was actually from an investment banker in Harvard Business Review. So for as much grief as we might give business people or bankers, they have a pretty darn good understanding of complex systems compared to some biologists or clinicians. So obviously, many people are aware of some pretty amazing technical advances in molecular biology, particularly via next generation sequencing. So next generation sequencing, that's a picture of an Illumina machine, which is one of the leaders in next generation sequencing. Obviously, you have a world leader in BGI here in next generation sequencing as well. What's amazing about next generation sequencing is that it's this technology that's progressed at the super Moore's law rate. You're rare to find many technological advances that will progress that fast. Just under 2 decades ago, a human genome cost $1 billion, and now we're to a point where it's effectively about $100 to sequence a human genome, plus or minus. Amazing orders of magnitude difference. And genome sequencing technologies are giving us an unprecedented high-dimensional view of the human body. We're not only able to sequence single individuals, we're able to sequence individual cells inside the body. So what is this high-dimensional view of the human body revealing to us? Well, it's revealing kind of what we might expect is that where this complex system of networks that are connected at various levels. So just think about a single cell for a moment in the body. One cell has 3 billion base pairs of DNA, right? That's wrapped in this three-dimensional structure. You learned about chromosomes in a previous talk. These 3 billion base pairs of DNA express RNA, and some of those RNAs make proteins you might have learned in your high school or college. But of course, it's not that simple. That's sort of like the Rutherford model of the atom. Actually, it's the DNA expresses many, many different types of RNAs, picoRNAs, link RNAs, mRNAs. They interact with each other in a network. They go back and bind to the DNA and regulate the DNA. Some of those RNAs make proteins. Proteins interact with each other and form networks. We'll go back and that network will interact with the DNA, with other elements. So inside one cell, we have a whole constellation of just millions of different types of interactions, different types of networks. Of course, cells organize into tissues. There's cell-to-cell communication. It's another network. Tissues form organs. There's organ-to-organ communication. That's a different layer of network. And of course, if everything in that little box that you see there is all we had to worry about, life would be somewhat easier. But we have, of course, the environment interacting with this complex system from all sides. So this is why it's so hard to translate knowledge of genetic factors that cause disease into therapies, because we really have to consider this whole system. So with advances in genome sequencing technology, we're obviously sequencing many more things and sequencing many more diseases, and there's a lot of data out there now in the world where we've measured sort of the molecular characteristics, the signature, if you will, of many different diseases. So one of the things I did actually back when I was a graduate student at Stanford was to collect a lot of the disease genomic data that was being published and actually put on the internet, and to ask a question. And the question was, now that we have all this molecular data on disease, does the molecular taxonomy or the molecular sort of tree of relationships of disease look anything like the symptoms and anatomy-based taxonomy of disease that we still organize our health systems around today? So what you're seeing here in this picture is that if two diseases represented by the nodes are connected, that means at a genome-wide level, the genes that are disrupted in the disease are more similar between these two diseases than you'd expect by chance. And when you do this sort of data-driven molecular taxonomy of disease, you find some very unusual things. For example, I don't think I can point, but if I could, in the upper right-hand corner, you would see that Alzheimer's disease at the molecular level looks somewhat like actinic keratosis. Actinic keratosis is actually a skin disease. So we see brain diseases looking like skin diseases. And we actually find this over and over again, these unexpected connections. So probably what this shows is that our definition of disease, or at least the way we categorize it, is likely wrong. And we need to redefine it based on molecular characteristics. So we can actually take this idea of using data-driven approaches to redefine disease up to the individual patient level. So what you're looking at here is a figure from a paper we published in Science Translational Medicine in 2015. So in this case, you're looking at a network, but you're not looking at a network of diseases. You're looking at a network of patients. So what I did when I got to Mount Sinai, where I am now in New York City, is we have electronic health record data on about 5 or 6 million patients. So what I did is I wanted to use this data to explore this idea of a learning healthcare system, right? So we don't really have learning healthcare systems that use data on previous patients to inform the diagnosis of future patients, right? So what we created here is actually a data-driven map of all the individual patients. So what we did is we took all the objective, sort of quantitative data we had on the patients in the electronic health records. Think of blood test results, your height, your weight, a huge number of measurements, and I represented each patient basically by all the data that I had on them. And I ignored whatever diagnosis they might have been given by the doctor because I considered that to be subjective. I wanted quantitative data that was collected. So then I basically created that profile for each patient, and I said which patient looks like this patient looks like this patient, et cetera, and built a patient-to-patient similarity map across all the data we had measured on these patients. So that's what you're looking at here, is this sort of a map, if you will. And the question is, if I'm a new patient at our hospital, you can imagine a Google Maps dot or a Waze dot's blinking on this, and you want to know if you're in one position or another position, does it matter for your health? So what you see on this map is some colored regions. So then after we organize the patients based on their data, not their diagnosis, we then ask the question, where are all the patients with type 2 diabetes? So type 2 diabetes is a metabolic disease. It's thought of as being one disease, but what the highlighting here shows is that when you look at the patients from the data-driven perspective, that they're not all clustered in one area. In fact, if you just focus on the diabetes patients alone, you get these three distinct clusters. So the question is type 2 diabetes more than one disease? We think of it as one disease, and I can't go into the details too much, but the critical question, does it matter clinically if you're in any one of these clusters? And so what we found, for example, is that if you're a type 2 diabetes patient in this top cluster, you had increased risk of heart attack and stroke above the typical type 2 diabetes patient. What we also showed is if you're in the bottom cluster, you had an increased risk of cancer above the typical diabetes patient. And we actually found genetic markers, because we had genetics on some of these patients that would help bin patients into each of these different groups. So then we can come up with a more precise definition of what type 2 diabetes might be. So my favorite thing about taking data-driven approaches is it really helps protect us from what's called the streetlight effect, or only looking where the light is shining, right, to reveal the unknown unknowns. So I'm quoting Donald Rumsfeld in a scientific talk, which is a bit unusual, and if you don't know your recent American history, Donald Rumsfeld was actually Secretary of Defense at one point of the United States. He probably has no business being in a scientific talk, but he said a quote that I actually like quite a bit. And he actually got made fun of for this quote, but I think it's actually an insightful quote in some way, particularly the last line, which is there's unknown unknowns. There's things that we don't know that we don't know. This is really true in scientific research. We think of scientific research as discovering the unknown, but for the most part, the way science is practiced is to take established hypotheses and really sort of iterate on those rather than to focus too much on the unknown. So one great example of this is a study we recently published on Alzheimer's disease. It was a sort of a big data study analyzing Alzheimer's disease. I'll go into the details. But my favorite result of this study was this really silly quote that I got in the New York Times, which was, I went looking for drugs and all I found were these stupid viruses. What does that mean? That means is I was actually analyzing all this data to find drug targets. But what the data revealed was actually that viruses could potentially be causing Alzheimer's disease, which is a novel hypothesis for Alzheimer's. So before I go further into the study, let me explain to you what Alzheimer's is and why it's so important. For one thing, it's a neurodegenerative disease that steals people's memories. It's increasing across the world, and if any disease could bankrupt even the richest countries, it's going to be Alzheimer's disease probably. It's extremely expensive. We don't actually have really any way to treat it. So it's caused by many different factors, but if you look in the lower, or at least has many characteristics that are associated with it, but one of the critical characteristics is in the bottom right there is the formation of these amyloid plaques that form in the brain. You can actually image these amyloid plaques. You can do a brain scan and you can see them in Alzheimer's brains. So it's a characteristic finding of Alzheimer's, so naturally it became one of the critical hypotheses for trying to treat Alzheimer's disease. The idea was, hey, if we could get rid of these plaques, maybe we could reverse the disease. This is the amyloid hypothesis, one of the predominant hypotheses. Well, we've tried to do that. We've actually been even successful at removing plaques, but unfortunately that hasn't really done anything to treat the disease. In fact, there's over 300 failed over 2,000 failed clinical trials, 300 failed drug compounds. We've had so many failures in trying to treat Alzheimer's in this way that there's these articles appearing now. What if we're completely wrong about the theory of Alzheimer's disease? It's actually published before our study came out. So we took advantage of a really interesting data set, which actually is actually a public domain data set that anybody could really access if they applied. It's the National Institutes of Health in the United States formed this research project called the Accelerating Medicines Partnership for Alzheimer's Disease. That's a lot of words there, but it's really the most ambitious sort of big data study on Alzheimer's. So what they did for thousands of patients affected with Alzheimer's disease is they actually measured huge amounts of information, many different layers of information at the molecular level, like epigenetics, even microbiome, metabolomics, all these sort of different molecular characteristics, but also including things like clinical imaging, et cetera. You can think of it, which it is the largest collection of data ever measured from patients affected with Alzheimer's disease. So what we did is we actually started to tie all this data together. Now the problem is we don't know what the true model is to connect all this different data together, what the true mechanisms are. So we used a data-driven approach called Bayesian network inference. So in this cartoon, imagine that the green is a segment of DNA, and maybe the yellow is a pixel in an image, and maybe the purple is a protein, and we just start looking at how the data is varying across all the different data sets, and almost like a correlation network structure. And then we use the data to tell us how one piece of data might be related to another piece of data. But we don't just look at correlations. It's a complex methodology I can't explain in this short talk, but we actually can go beyond just correlation and look for directionality and try to understand how data might be flowing from one layer, say the DNA layer, even all the way up to other layers such as the imaging layer. So it's a complex calculation that has to run on a supercomputer. And we actually asked the question, then we built these networks for healthy brains and Alzheimer's brains, and we simply asked the question, what is happening in the rewiring of these molecular networks between healthy brains and Alzheimer's brains, sort of like the Yellow Emperor's book. We were looking for patterns of imbalance and how we could rebalance those patterns, and in this case, using drugs and molecular networks. So when we let the algorithm run, it took several days and weeks, and what popped out was something we didn't expect, which is we identified a specific molecular network that seemed to be rewired between the healthy brains and the Alzheimer's brains. And what was at the center of it was this gene related to this virus, HHV6A. And in fact, we found that it was interacting with known Alzheimer's genes like this gene PSEN1, which is a known Alzheimer's gene. So we didn't expect there was that at all that there would be the viruses in these brains, and beyond that, we didn't expect that they would actually be participating in networks related to Alzheimer's disease. HHV6 is a DNA virus as part of the herpes virus family. It's actually fairly ubiquitous in the population. It has an interesting characteristic in that it actually integrates with our own DNA in the subtelomeric regions. So some of the really interesting implications of this study are that first, there's a common viral species that's expressed in Alzheimer's brains on higher levels than healthy brains. We actually replicated this in several independent cohorts, so this is not something that's contamination. And this suggests some new opportunities or new hypotheses to treat Alzheimer's disease. I mentioned before that we've sort of run to the end of the course of the amyloid hypothesis, and that hasn't been successful. So this suggests that immune therapies or even antiviral drugs that exist already could treat Alzheimer's disease. There's actually a study that was conducted in Taiwan where individuals infected with herpes virus were followed over many years, and they tracked the antiviral therapy. It reduced the risk of dementia by 10-fold. So we're reading about all these cool scientific discoveries, as we often do, but one question people often think is, well, what does it mean for me right now, right? Because a lot of these discoveries aren't going to be translated into things that affect people for a long time. So if we're going to use the same methodologies we use to study Alzheimer's disease to really deliver personalized health care to the individual patient, well, there's some things we have to fix before we do that, right? Our healthcare system is actually not really designed for this type of data-driven healthcare, like the examples I showed you. These are real pictures from 1980 and 2018. coffee shops have had more innovation in the way they deliver service than hospitals, right? It's pretty shocking, these pictures, right? And one of the arguments I like to make about so-called big data or AI in healthcare, because you read about it in the news a lot, that we're really in the stage of building mechanical horses to pull a carriage. What do I mean by that is we have this new technology, artificial intelligence. We have a healthcare system that's operating using old technology. So we're forcing new technology to work in the framework of the old system, so we get a compromise solution. We're all building mechanical horses to pull a carriage. So one thing I'm very much interested in is how do we get rid of this carriage so that we can really realize this data-driven future of healthcare. So hospitals are really like mainframe computer systems from the 1970s and 1980s, right? Centralized equipment, privileged class of sort of operators who can manage the equipment. So one thing we've done, if my video will play, there we go, is we've actually, from the ground up, tried to redesign the clinic to support data-driven healthcare. So this is a clinic called Lab 100. It's a real clinic we've built at Mount Sinai in New York City. It's a new type of clinic that collects millions of data points per patient encounter and actually creates a better experience for the patient when they participate. So one of the key questions we're trying to ask in Lab 100 is, what if we actually had a health record? By the way, we don't actually have health records. You hear the phrase electronic health records, but we actually have records of your diseases and your treatments. What if we actually had a health record? What would we measure and why? So this is actually, I just have a few slides left. I'm almost out of time. This is actually the initial patient consult area when you come in. And by the way, this is all real. This is not a demo. This is a clinic that's open to the public in a week. This is not a 3D rendering. This is a real clinic we've built, and we've seen several hundred patients already. So it's in beta testing. So this is the initial consult area. This is sort of what it looks like. We put all your data in these data dashboards. Every time we show your data, we show where you are on the distribution of people like you, your ethnicity, your age, your region, et cetera. So you don't just see a number, you see where you fall in the population distribution. We measure things like balance. A lot of accident mortality is caused by people falling, so balance is important to measure. We do blood testing on site, and actually the blood testing results are done before you're done with a visit. Every time we measure something on you, it is instantly interpreted and displayed in front of you, right? Think of the current doctor office where they take your blood and they'll say, we'll call you in 1 or 2 weeks if something's wrong, right? That's not how it works in this clinic. Instant gratification is what we expect now, right? So even blood testing's done. We do a cognition and battery cognition test to get mental baselines. We do 3D body scans. And when you go through all these different stations, I haven't shown all the different stations, all of your data is instantly synthesized and displayed in this data dashboard, and the doctor, instead of being a data entry clerk at a computer, actually has a conversation with you when they have a story about all your data. And so this is actually one clinic we've built in Mount Sinai in New York. If you can come see it if you come to New York. But one thing I want to tell you is that it looks very permanent, but it's actually something we built in about 2 weeks. We actually designed this clinic to be modular and scalable, because one clinic at Mount Sinai in New York is a very boring vision, right? So we actually are starting to work on concepts for Lab 100 in the workplace, Lab 100 in the retail, because my vision and my dream is that we've created a new internet of healthcare that's powered by these distributed smart clinics everywhere. We need to create a new internet of healthcare because the incumbent health systems are not going to do this, right? We need to create a new system that challenges the incumbent system, right? And we actually have an artificial intelligence software that underlies Lab 100. I didn't have a chance to talk about it too much today. We published a paper called Deep Patient and others where you can read about it. And I really hope that this is something that could be a global internet of healthcare, right? Just like every self-driving car, when a self-driving car drives a mile, it's connected to a system where it gets to share the experience of driving that mile with all the other self-driving cars that are connected. So it's my dream that we have all these clinics, and every patient we see shares the experience of that patient with everyone around the world. The healthcare, the internet as we know it today, is shared knowledge around the world, right? So let's build an internet of healthcare that shares health around the world with everyone too. Thank you. This way.